constraint, which is quite amazing. Okay, anyway, so to resolve, as I've already said, to resolve j of t, comma n, we need to take the inverse Laplace transform of this function. Remember, we're converting s back to t, so everything here that doesn't involve s is just a constant, so we can bring it out the front, and you'll see here, which is what we've done here, and we're remaining with the Laplace inverse of s to the power of n minus m plus 1 over n subtract 2. Okay, so as I said, this is an incredible, if you've dealt with Laplace transforms before, you know that this is, an incredibly easy inverse Laplace transform to evaluate as long as this power here satisfies certain constraints. So let's go through that. So the definition of the Laplace transform of t to the power of a, in general for any value of a, so not dealing with just integer powers, is equal to gamma of a plus 1 over s to the power of a plus 1. So if we rearrange that term, that is the same as the inverse Laplace transform of 1 over s of a plus 1 is equal to t to the power of a divided by gamma of a plus 1. Remember, this is just a constant, so I've just divided it onto this side, and that's what we have here. And so therefore, if I just replace a plus 1 with b, we have that the Laplace inverse from s to t of 1 over s to the power of b is equal to t to the power of b minus 1. As I said, just rearrange it. A plus 1 is equal to b over gamma of b. And I've done that just because that's more similar to the form that we have. Now, this only holds when a is greater than negative 1, or equivalently, remember we're dealing with b is equal to a plus 1. That's when b is a positive value. So, let's have a look at our situation and see whether or not the term that we have with the restrictions that we have imposed on n and m will actually allow us to take this inverse Laplace transform. Okay, so s to the power of n minus 1 plus 1 over n minus 2 is obviously just equal to 1 over s to the negative of it. So I've just taken this and made it to s to the negative power, which just swaps these around because there's a minus sign there. So s to the 2 minus n plus m plus 1. So that means, remember, that our condition here, we now have it in this form of 1 over s to the power of b. Our b function, well, I guess it is a function, but our b value is 2 minus m plus 1 over n, and we need b to be positive. So that's what we have in this step here. 2 minus n plus m plus 1 over n must be greater than 0. So remember that n is a positive real value, so that means I can multiply through. And so if I multiply both sides by n, I get 2n. So let's say I put an n out the front, open brackets, close brackets. I then have n times by this minus n times by that. So I have 2n. And then if I multiply this component here by n, obviously it just cancels out with what we have here. And so you're just left with n minus n plus 1. So therefore, if you rearrange that, and that must be greater than 0, If you rearrange this, 2n minus n is just equal to m. And then if we have a negative by a negative here, we have a positive. And so then we have n plus n. And then on this situation here, we've got the negative times by positive 1, which is positive 1, must be greater than positive 1 here. So I apologize. I've actually made a slight mistake here. This should be positive 1. So because remember here, if we bring this negative to here, this becomes a negative 1. And then if I plus it onto this side, that should be a positive 1. So my apologies here. That should not be negative 1. It should be plus 1. Now, as n and m are both greater than 1, if I add them together, I have a value that is greater than 2. So therefore, we know that it satisfies the constraint that it's greater than 1, because if n is greater than 1 and m is greater than 1, then if I combine those two together, I know that definitely it's greater than 2. And so the condition, remember again, this should be positive 1, is satisfied in this case. So by imposing this restriction here, which initially came about for convergence of the integral, that then also allows us to equally take the inverse Laplace transform using this form, which is great, which means that we can get our solution very easily. Okay, great. So therefore, excuse me, j of t comma n, which is equal to, so this expression that we had here, times by the Laplace inverse of the s term. Remember, all I've done here is I've just transformed it into the form of 1 over s, which is what we've got here, is equal to, so we just have that term from before, times by t to the b minus 1. So remember, in this case, b is equal to 2 minus n plus 1 over 2n, which is what we've got here. Subtract 1, so remember, that's the b term. Subtract 1, which is what we have here, divided by gamma of b. And all I've done is taken the b term here, which is this, and put it into the gamma as required. And then all I've done in the next step, this obviously remains unchanged, so that just stays as it was before. What we have on the bottom, excuse me, well, we have the bottom with the gamma function. This remains unchanged, but we can clean this up slightly. Obviously, 2 subtract 1 is just equal to 1, so we have 1 minus this. Okay, great. So now we've got our j of t, n, n. So that is this function that we have here. So, ideally, we should really just leave it there because that's an even more generalized case than what we have with this one here. Because not only does it include an n and an m term, it also includes for when we've got it for t. But anyway, because we're dealing with a special case, which is when t is equal to 1, so we get this integral, we just need to plug that in. Now again too, because of the way in which this integral under the Laplace transform converted into this form, which allowed us to use this integral, which allowed us to call upon this integral, I should say, which isolates a out, that therefore made it very, very easy to do the inverse Laplace transform with a t term. When I plug t into 1 into this, it just disappears. 1 to the power of whatever, as long as it's a real value, is just 1. So we've solved it, and it's so easy. Okay, so let's do that. So I of n comma n is equal to j of 1. So remember when we evaluated t is equal to 1, n comma n. So we have this component here, which is what we have here. And then you'll see here, where there was t before, I've just replaced it with 1 to the power of 1 minus n plus 1 over n divided by the term that we had before. That's just 1. And so putting it all together, we have, so I've taken this term, and I've put it on the top, which is what it should be. You'll see here, I apologize, there is a slight error. This n here should be down the bottom here. So just remember that when you're looking at this. I just made a slight latex typo when I was writing this up. So just remember that should be down there. Divided by 2n, so that's the 2n comes from this component here. And then remember we also have this division here. So we have this component here, which is gamma of 2 minus n plus 1 over 2n. And so finally, we see that I of n comma n, which is equal to this integral, the integral from 0 to infinity of sine of x to the n over x to the n dx is equal to this term here over this term. Remember the mistake that I made on this line is that it should be down here, which you'll see that has been corrected here, is equal to gamma of 1 minus n plus 1 over 2n times by gamma of n minus 1 plus 1 over 2n over 2n gamma of 2 minus n plus 1 over n. So although this is a rather complicated expression, we now, as long as you're comfortable with expressing your solution in terms of the gamma function, we now have an expression that allows us to evaluate the integral for any two values of n, as long as they're both real values and they're greater than 1. So anyway, that's the end of this integral. As I said, I strongly encourage everyone to not only go through this themselves, but to equally jump into the link that I'm going to have down for method 3 of dealing with the special case of when n and m is equal to 1, where I applied Ramanujan's master theorem, and see if you can use it in order to evaluate this integral and see if you get the same result. You may get a different form. I believe you will get the exact same form, but hey, you never know, you might get a completely different form, and we could then use that to form some sort of a nice equality that will occur between the two. Okay, anyway, I do apologize. I have a tendency to waffle on and get overexcited. I just absolutely love this stuff. So again, too, just a quick reminder, remember there's the error there, where the n should be down there, and the other error was that this should be a positive one. Other than that, unless I've forgotten something, and I'm pretty sure I haven't, everything else is spot on within this. So anyway, I hope you've enjoyed this video. If you have, please hit like. If you would like to see more videos like this, I release them generally 2 times a week, and I try to aim for minimum of 2, and then usually, well, any maximum, but usually about 4 integrals. And so if you like to see these sorts of things and you want to see more, please consider subscribing or subscribe. If you have any requests of certain integrals that you would like to go through, please either comment on this video, send me a direct message, and if I'm able to solve it and I have time to solve it, absolutely I'll put a video together. So other than that,